since you are having current source as well as you are going to apply an voltage source, you can easily use KCL. So you can use KCL and find what is the current I. So I will be equal to V by R naught. See this, you can apply Kirchhoff's voltage law at this, Kirchhoff current law at this node. One current GMVI is coming, one current is going like this, and this current from the voltage source is also coming. So two currents are coming, one current is going out. So GMVI plus I equal to the current through this R naught. You know voltage across R naught is V. So current through R naught is V by R naught. So GMVI plus I is equal to V by R naught, or I is equal to V by R naught minus GMVI. Simple KCL equation. Okay. So I'm just applying Kirchhoff's current law and I am finding what is I. Again you see here V by I is R naught F, but here I have V, but here I have VI. So I need to bring V inside here. So go back to the input side. So you know when you made Vs equal to 0, apply KVL in this loop, you get Vi plus Vf equal to 0, or Vi equal to minus Vf. And Vf is equal to minus beta I naught. And you know that I naught is flowing outside, I is flowing inside. So Vi will be equal to beta I. I naught will be minus I. Okay, I naught and I directions are different. See here. See, I is because of voltage, what you apply capital V, the current will be flowing inwards. But I naught is originally, I naught is the amplifier current, which is actually assumed to flow outwards from your amplifier. So I naught and I are opposite in direction. So I can write I naught equal to minus I. So substitute everything in the input KVL equation. So input KVL equation is Vi plus Vf equal to 0, or Vi is equal to minus Vf. So Vi is equal to minus beta I naught. But I naught is minus I. So Vi is equal to beta I. Substitute the value of Vi equal to beta I in this equation. So I is equal to V by R naught minus beta into Gm into I. Okay. Vi is beta I. So you can bring this term is having I, bring this term here. So I plus beta gm I equal to V by R naught, or from this I take out I outside, I into 1 plus beta gm equal to V by R naught, or cross multiply V by I is equal to R naught into 1 plus beta gm. So V by I is going to be R naught F. So R naught F equal to R naught into 1 plus beta gm. Here you see this GM is representing without the load. As always, remember when you suffix with small letters, it is without the load. When you suffix with capital letters, it is going to be considering the load. So we have proved here R naught F equal to R naught into 1 plus beta GM. So your output resistance is also increasing by the same factor 1 plus beta GM. The voltage series feedback, the previous example, the input resistance was increasing, the output resistance was decreasing. That is what an ideal amplifier requires, right? So input resistance should be very high, output resistance should be very less. Then only the proper amplification and transfer of power from the amplifier to the load will take place. But in current series feedback, input impedance is very high. That is very good for me. But output impedance is also very high, which means that the amplifier cannot give out large current. So when the resistance at the output side is very high, naturally the current will be very less. So this amplifier is not suitable to provide large current because the resistance at the output side is very, very high. Remember, always in feedback amplifier, we'll find one resistance R0F with feedback, and we'll find one more resistance R0F dash considering your RL. See, this R0F is here without your RL. Before itself, I measure R0F. And when you measure considering RL, here you will be having R0F dash. You consider RF, when you consider RL, it is going to be R0F dash, and always blindly it is going